Find the equivalent torsional system for the system given in the figure. So the configuration that is given is a rod which is hinged at one end. This is a slender rod, and there is a block of mass M. This is a block of mass MP at its very end, and the angle that this makes is about theta. This slender rod is connected to a spring of stiffness K at 2/3 of its length. This is 2L by 3, and the remaining length is then equals to L over 3. So we want to find the equivalent system for this torsional configuration. We are going to use the kinetic and the potential energies. So the kinetic energy of the system, T, can be written as equals to the rotational, that is half I theta dot square of the slender rod plus the translational energy of the rod, that is half mv square, plus the translational energy of the block of mass, that is half mp vp square. So you know that for the slender rod, I is equals to 1 by 12 ml square, right? And then you have got theta dot square plus for the translational kinetic energy or velocity, what you will have is half m. In terms of theta, you can write the x as equals to the total length of this mass divided by 2. Okay, so the total length is L and over 2 halfway, and then that is theta dot square. For the block of mass M, you will have the entire length of the rod, that is LP, or just the L, you can say. You can say simply L because the length is same. Okay, so this is L times theta dot square. So if you simplify this, you will end up with half 1 over 3 ml square plus mp L square theta dot square. So this portion over here is your equivalent rotational mass, or the equivalent moment of inertia of your system. Okay. Similarly, you will have to find the potential energy of your system. So to do that, let's first derive the equation for potential energy. You know that there is a spring attached, so that spring will store the energy in the system. So let's say that is half kx square for the spring. So the spring is attached about 2/3 of the length, so the spring will be 2/3 of the length times theta. So x will be equals to 2/3 of the length times theta, square plus the mgh value of the mass of this slender rod. So the mass will be equals to about L by 2 times the height will be equals to, or the datum will be equals to L by 2 times 1 minus cosine theta. Okay, so it's going to act at the center. The datum will be taken from the center of this rod, and then 1 minus cosine theta is the angle that it makes, plus mp g L times 1 minus cosine theta. For small theta, you can write cosine theta will be equals to 1 minus 1 over 2 theta square. So then V is equals to 1 by 2. If you simplify the whole equation, you will end up with 4 by 9 kl square theta square. This is the half kx square term, plus the mgh terms, one for the rod and one for the mass. So plus mg L by 2 times half theta square plus mpg L times half theta square. So ultimately you will get V as equals to half times 4 over 9 kl square plus mg L over 2 plus mpgl multiplied by theta square. So this whole term will be then the equivalent stiffness of our system. So this solves the problem.